Hello everyone, my name is Hossein Keshtkar and I'm a research assistant at the Centre for Compressor Technology here at City St George's University of London. And welcome to this week's Lecture Tuesday, where we'll be talking about oil-injected screw compressors, their benefits and their drawbacks. Screw compressors are widely used in a broad range of industries such as refrigeration, automotive, pharmaceutical, food packaging, and generally anywhere we need constant flow of reliable compressed air. As we know, a screw compressor is primarily made of rotating screws which trap and compress the air as they rotate. Commonly, they are referred to as male or female rotors based on their operating process, in which the male drives the female rotor either by direct drive or synchronizing gears. A way of categorizing screw compressors is by their oil injection or oil-free characteristics. In oil-free screw compressors, the rotors rotate without any requirements of oil medium inside the chamber, whilst in oil-injected compressors, a flow of oil is introduced into the compression chamber as they rotate. The oil is injected via injection ports and fills the compression chamber as they rotate. Here we can see a cool oil in blue color being injected and guided towards the discharge end of the compressor as the rotors rotate. You may ask, why is oil injected? Well, oil injection is used for various reasons, but mainly for lubrication, sealing, and its cooling effects. As we imagine the rotor profile shown here in 2D, the need for lubrication to prevent wear and damage seems very sensible considering the material of these rotors, which is commonly steel or similar alloys. The rotors could even have coatings and may be in direct contact with each other, and they certainly will for direct drive screw compressors. Thus, having sufficient lubrication at these points of contact is quite essential. The second important factor is sealing. Leakage can happen between the rotors and the casing and between the rotor lobes themselves. This can be minimized by introducing oil to improve the sealing capabilities. Due to the natural existence of the clearance gap in the rotors, we will have some internal leakage of the flow, which is quite unavoidable. Having oil injection can seal this clearance gap, significantly reducing this internal leakage. We can see in this animation that as the air is being compressed inside the rotating compression chambers, it will have tendency to leak from high pressure chambers to those of lower pressure. Also, due to the rotor material, it isn't practical to completely seal the gaps of the rotor profiles as they could have unwanted contact and wear over time. But having a fluid such as oil inside the compression chamber can significantly seal these small clearance gaps, thus reducing internal leakage. But perhaps most importantly, oil injection cools down the gases inside the compressor. Direct contact of oil with the trapped air, which is increasing in temperature as it's being further compressed, will cool it down significantly. There are obvious benefits of this action, such as preventing the compressor from overheating, reducing thermal load of the compressor, and also all the components downstream, and etc. But essentially, considering the small clearance gap around the rotors, any excessive heat that may cause the material to expand could potentially increase the risk of contact damage, and avoiding this problem is crucially essential. Thus, perhaps the major role oil plays in injection machines is the cooling down effect on the compressed air and the compressor material. In the bottom animation that I'm about to show, we can see the compressor in action as it's compressing the air. As the air is being pressurized, it's changing its color from blue towards yellow and ultimately red. The red regions are showing regions of the compressor that have the highest pressure, which is towards the discharge end. In the top animation that I'm playing, we're seeing the exact same compressor in action, but this time we are seeing the temperature distribution. We can see that as the oil is being injected, it's being guided towards the discharge end as the compressor is working. We can also see that the oil is changing its color from green towards yellow and ultimately red, showing that it's absorbing heat as it's being compressed through the compressor. And we know that as the oil is absorbing heat, it's actually absorbing heat from the compressed air, thus cooling down the air that's being compressed. Well, the benefits of having oil injection is quite amazing. So what are its drawbacks? First of all, by involving oil in the compression chamber, we will have drag forces acting on the rotors. This will lead to mechanical losses and prevent the compressor from running at high speeds. Having an oil-injected compressor, we would obviously need extra requirements for oil maintenance and services. Also, the constant need for a reliable oil circulation loop is essential. Plus, we would need extra space to house the oil circulation facilities. With oil injection, we would most likely have some degree of oil contamination in the discharged air, which basically means a carryover of oil in any form, such as vapor, mist, or small particles in the delivered compressed air. To avoid this, we can go for oil-free compressors, although they're more complex in their design and they have potential sealing issues, and also come at a much higher initial price and usually have a lower pressure ratio. Another drawback of oil injection is the possibility of oil-related flashing effects. Flashing basically means the rapid phase change of a fluid, absorbing heat and cooling the medium down. Oil contamination can affect the flashing effects of a gas in certain applications. We mentioned oil contamination. So what if we have some oil carryover in the compressed air? I mean, who is it going to hurt? Well, this strongly depends on the target application. For example, in areas where we have food industries, pharmaceutical processes, medical equipment, or other sensitive health and medical sites, or even more broadly, generally, wherever we need absolute clean air, it's important to essentially avoid any oil carryover. Also, for special applications such as refrigeration, which will be impacted by dilution effects, it's important to go with completely clean air. Refrigeration cycles rely on the flashing effect of the refrigerant to operate. Thus, any oil dilution in the refrigerant vapor will impact this effect and reduce the refrigeration capacity of the system. In this table, we can see how air classes are determined. An air class of 0, which refers to the highest quality of air, which is essentially just pure air. An air class of 1 resembles air with a quality of 0.01 milligram of oil carryover per cubic meter. And an air class of 5 would resemble compressed air with an oil concentration of 5 milligrams per cubic meter, resembling a significant amount of carryover in the compressed air. But essentially, there is no good or bad compressor type. This is chosen based on the application. Each compressor category, whether being oil injected or oil free, had its own merits and its own purposes, and this is chosen based on the target application. To conclude our discussion so far, we have to point out that because oil-free compressors need to have synchronizing gears and seals between the bearing and the compression chamber, which can make that solution very expensive. Thus, about 83% of all screw compressors in action today can be classified as oil-injected screw compressors. In principle, oil injection is considered beneficial from compressors' operational point of view. However, the oil may have adverse effects on the target application. Oil-free compressors are more complex generally than their oil-injected counterparts due to their special requirements for sealing and are significantly more expensive. So, can we use oil injection and then remove the oil? Well, yes and no. Oil filtration and separation can be introduced, although not perfect, but they can do a good job minimizing the oil carryover. But the feasibility of this would directly depend on the quality of air required and the target application. For strict air quality and specific applications, we have no choice but to go for oil-free compressors. Or for cases in which we have sweet or sour gases compressed, involving oil can protect the rotor surface by reducing or eliminating corrosion issues, which may prevent the need for expensive material such as stainless steel or other special rust-sensitive material. Thank you for listening. With that, we conclude today's short lecture. For any further discussions and questions, please get in touch and stay tuned for our next week's short lecture episode.